Okay, this video is about the pH scale, and you're probably pretty familiar with the pH scale from like year 7. You're doing it all the time. Okay, so you know that pH 7 is neutral, pH 1 is a strongly acidic solution, whereas if you had like pH 4, that's going to be weakly acidic. And when you get to pH 14, that's strongly alkaline, and say pH 11, you know, it's going to be weakly alkaline, and so on. You also know about indicators. Indicators are substances that change color depending on the pH, and the most commonly used one is like universal indicator, which is actually a mixture of different indicators. I'm sure you're aware of all the colors you can get for that: green for neutral and red for acidic and so on. But universal indicator is not the only indicator. There's actually lots of indicators. Another very common one is litmus. That doesn't give you such a good color range. So litmus is going to be red in acid, blue in alkaline, neutral. It's a mixture of red and blue. So there are lots and lots of different indicators. Anyway, we want to talk more about pH rather than another way of measuring pH is with a pH meter. So it's like an electronic device. You put it in a little probe, and it will give you a readout, usually to 2 decimal places, what the pH is. Okay, so let's think about what it actually means then. Okay, well, we probably know now that acidic solutions contain H plus ions. So you've got quite, okay. Now, the higher the concentration of H plus ions, the more acidic it is. And alkaline solutions, they contain OH minus ions. Right, if you mix, we also know that if you mix acidic acid and alkali, you get a neutralization reaction. And what happens is you're adding H plus from the acid, hydrogen ions, you're adding OH minus ions from the alkali. They will join together to form H2O, covalent water. And you can see that this is not only balanced for the number of atoms, you've got 2 hydrogen atoms on the left and 2 on the right, 1 oxygen and 1 on the right, but it's also balanced for charge, because if you add up all the charge on the left, that comes to 0, and obviously the charge on water is also 0. So it's balanced for numbers of atoms and for charge. That's what happens in neutralization. So for example, if we added, hydrochloric acid, you can't get a bottle of just H plus ions. It's got to come with a negative ion. So if we had H plus ions and the negative ion to go with it, Cl minus, that would be hydrochloric acid. And likewise with NaOH, you can't have, with hydroxide ions, you can't have a bottle of just negative ions. It's got to come with a positive ion. So most commonly we'd use sodium hydroxide there, so it would be Na plus ions along with the OH minus ions. You'd get water when they're neutralized. And what would be left over, I think we've seen before, are the Na ions. They're spectators. They don't actually change in the reaction. And chloride ions, the negative ions, they don't actually change either. But you see, you've essentially formed a solution of sodium chloride of salt. Okay, so that's neutralization. Let's have a look at the numbers then. Okay. All right. So what this pH number here, pH1, means is that the concentration of hydrogen ions, so hydrogen ion concentration is equal to 0.1, and the units are moles per decimeter cubed. That's the unit of concentration. If you haven't done that yet, don't worry about it. It's just simply a unit of concentration. Now at pH 2, that is actually, every time you go up a pH unit, it becomes, the hydrogen ion concentration becomes 10 times weaker. So the concentration of hydrogen ions at pH 2 is 0.01. It's a tenth of what it was there. And when you go to pH 3, the concentration there is going to be 0.001 moles per decimeter cubed. And 4, 10 times weaker again, so it was 0.0001. Now there, it gets a bit silly with all these zeros after that, so it's much easier to write that in standard form, and you write that in standard form as 1 times 10 to the minus 4 moles per decimeter cubed, or the units again, just to remind you what does have a unit. This would be 1 times 10 to the minus 3. This one would be 1 times 10 to the minus 2. That would be 1 times 10 to the minus 1. Now at pH 7, you can probably, if you just follow that, that's 1 times 10 to the minus 5 for that one, 5. 1 times 10 to the minus 6 for that one. And this is 1.0 times 10 to the minus 7 is the concentration of hydrogen ions in neutral water. So you can probably see where those pH numbers are coming from. They're coming from this like indice up here, yeah? Minus 7, pH 7, minus 4 for pH 4, minus 3 for pH 3, and so on. That's where they come from. Right? It's worthwhile remembering that, but you will never be asked that probably at GCSE. I've told you a little bit more than you need to. What you do need to know at GCSE though, is that when you go up 1 pH unit there, the hydrogen ion becomes 10 times weaker. If you go up 2 pH units, say from 1 to 3, it becomes 100 times weaker. If you like 10 to the power of 2. If you go up 3 units, it's going to become 1,000 times weaker, and so on. So 1 pH unit, if you go up 1 pH unit, it gets 10 times weaker. And that's called a logarithmic scale. You may have heard of that before. Logarithmic scale. And you may have come across them before in, I think, earthquakes, the Richter scale in geography. If you have an earthquake of 7 on the Richter scale and then you get one at 8, that's actually 10 times stronger than the one at 7. So they are used quite a few places. Okay. So that's all you really need to know. But just to fill in a little bit of extra detail now. So as long as you understand that, that's fine. But what about the OH minus ions? Well, you don't really need to know this, but of course, the higher the OH minus ion concentration, the more strongly alkaline it is. And at pH 14, well, that is OH minus ion concentration of 0.1 mole per decimeter cubed. And when you go to pH 13, right, that's 10 times weaker. So that's going to be 0.01 mole per decimeter cubed for the OH minus ion. And 12.001. Keep going all the way down to pH 7, and the concentration of hydroxide ions there is actually going to be 1 times 10 to the minus 7. Okay, which is, and if you look at neutral there, look, the concentration of hydrogen ions and hydroxide ions are equal to each other. That's what a neutral solution is really. Okay, now again, switch off if you don't want to, but just don't really need to know this just yet. But let's just write down what's happening in water. In water, you have H2O, it's covalent. But I'm going to draw this reversible arrow, means the reaction can go backwards and forwards. A tiny amount of water is always split up into OH minus and H plus ions, just a tiny, tiny amount. Of course, we've seen before, if you get lots of OH minus and lots of H plus, what will they do? They'll neutralize, they'll go back to form water. But every glass of water you pick up will have a tiny, tiny amount of OH minus ions and H plus ions in it. And that's why pure water will actually conduct electricity a little bit, even though it's covalent. And it shouldn't really do that if it's purely covalent, because it's got tiny amounts of ions in it. And as I say, at pH 7, the concentration of those ions, the OH minus, which makes it alkaline, and the H plus, which makes it acidic, are equal to each other, but they're both very, very small, like 1/10 millionth is the concentration there. Okay, I think we'll leave that there. But the main thing to realize is, pH, when you go at 1 unit, the hydrogen ion concentration is getting 10 times weaker.